Yeah, hey there, hi all. Yeah, so I think I can share my screen then. Yeah, so here we go. So can you see the screen right now or, yeah? Okay, so then I think we can start discussing homework number 3. So regarding classification. So let's go to our GitHub repository and read once again what we need to do. So basically in this homework, we will work once again with New York City Airbnb open data that we worked in the previous one. So basically, I will not tell you once again regarding how you can get the data. So either you can, use Kaggle page or can download it directly via link. So we will skip this part. So what will be different in this homework if we if we will compare it to the previous one? So so basically we will work with additional 2 features called neighborhood group and room type. So there are 2 categorical features. Basically there will be let's say quite important features for some of the questions that we will solve. Yeah. So basically the whole feature set, the whole features looks like that. So with our neighborhood group and room type. So also with our old features and our target variable price. And also we need to, before we start, we need to fill the missing values with 0. So we remember that we had the feature with missing values. And we need to basically kind of fill it with 0 values, which we will do later on. So let's start from the question 1. Question 1. So what is the most frequent observation mode for the column neighborhood group? So let's go to our notebook. So first of all, we will import the necessary libraries. So it will look like the previous homework. So we will use pandas and numpy, and we'll use matplotlib and seaborn for visualization purposes. So we start with the data import. So with addition to the old features that we use, we basically add the 2 new ones, room type and neighborhood group here, and use the read CSV function from the pandas library to read the data with the necessary column. So we check the shape of the data. So here are our 2 additional columns, and here how our data look like using the pandas head function. Yeah, so here it is. And then we need to, so we already know from the previous homework the feature with the non-value, so it's reviews per month, and we can just use the pandas function fill NA and fill it with 0 values, so like that in one row basically. So the first question is frequent values, and we can basically solve it in 2 different ways, like 2 main different ways. So the first one, we can use the describe function from pandas libraries with the addition called with the additional parameter called include. Calculate this function describe only for object variables that in our case would be neighborhood group and room type. Yeah, so because the categorical will be different from the numerical one, so meaning that we will have the different statistic types here. Yeah, so count, unique, top, and frequency. So basically the top is already here for the neighborhood group. It will be Manhattan. Yeah, so this is the first option how we can solve this task. Yeah, the second one is also using the mode function. So basically I use the mode function from pandas library. So you also have the opportunity to use, for example, SciPy realization of this function, and also calculate the modes like that. So basically you can see that the result will be the same, it's Manhattan. So the answer for the question 1 will be Manhattan. Yeah, so do we have any questions for this, or Alexei?
Yeah, there is a question, why didn't we have to fill all missing values with 0? And I think the answer is because there is only one column that hasn't values, right? And this is what we looked at in the previous homework.
Yeah, I think this is like the new person who didn't do the homework for the previous one. Yeah, so exactly, we have only one feature column with none values. Yeah, so then I think we can go to the next question. So the next question, so basically before go into that, we need to read how we will work later on with the data. So we need to also, as in the previous homework, split the train validation test set into 60 to 20 to 20% distribution. But in this case, we can use the train test split functionality by the from the scikit-learn library. Yeah. Yeah, so make sure that our target variable is not in our feature set. Yeah, so we will use it like that as a basically distinct target variable. So question number 2, create the correlation metrics for the numerical features of your trained dataset. And basically, what are the 2 features that have the biggest correlation in this dataset? So, and here is the example of how the correlation metrics for the dataset should look like. Yeah, and yeah, so here it is. So let's go back to our homework. For doing that, so I prepared the kind of copy. So I copied the data frame and called the new data frame called data numeric. So which will contain only the numerical columns. And here is the describe function, so how it's look like. So here you can see that we only have the numerical features inside, and then we basically can go to the exact step of calculation of correlation. Yeah, so basically we can use the core function, yeah, so basically in one row we can immediately have this correlation matrix, which will have ones on the main diagonal. Yeah, so and in the other cells we will have the corresponding correlation for the pairs of features. This is basically, let's say, kind of our kind of main correlation metrics, and then we can basically use a couple of ways how to find the biggest correlation. So the first option, we can just plot this correlation metrics. So for that, it's really easy to use the heat map functionality from the Seaborn library. So and just put the correlation metrics inside and then just plot it. So you can see it like that. So here it's basically our heat map representation of our correlation metrics. We also have ones on the main diagonal, and we also have the corresponding correlation for the pairs of numerical features. Yeah, and what is actually really nice here, that we can also differentiate from the color intensity. Yeah, so and we can immediately see our guys. So basically the biggest correlation. So it's reviews per month and the number of reviews. So 059, which actually makes sense in terms of like a logical thinking, that reviews per month and number of reviews have quite good correlation between each other. Yeah, so here they are. Or basically we can go to the different approach and can make it like that, for example. So we also calculate the correlation metrics using core function, then using a function called unstack and function sort values to sort our results, to sort our correlation for numerical features. So, and here is the result. So ascending false. So we have the biggest, which is basically the equal features. So then we are not very interested in that. And here is our winner. So we can also see that. So it's number of reviews and reviews per month that are having the biggest correlation. So this is our pair that we are interested in. And basically this is the answer for our question number 2. So it's number of reviews and reviews per month. Yep.
You can explain a bit what unstack does. So how do we go from a data frame where we have features in columns and features in rows to these pairs? So maybe you can just quickly show what unstack produces.
Yeah, so basically the idea of unstack is the fact that after, so we, if you can see this line, so we apply unstack after we have the correlation matrix itself, yeah, and then basically the purpose of unstack to actually, let's say, revert this correlation matrix into the pairs, yeah, that we will actually can work and using sort values function that we actually can order in a descending or ascending sort, actually. So this is basically how the unstack is working.
So we turn in a data frame into pairs,
yep.
Column name, row name, value, right?
And then basically we can apply, so the final step, we can apply sort values to order the result.
Yeah, thanks.
So any other questions maybe, or can we go further? Or okay, so then we can go further, and basically the third question, we actually need to apply our preparation from this part, split the data, but let's also check the question. So question number 3, calculate the mutual information score with the binarized price for 2 categorical variables that we have. Use the training set only. Which of these 2 variables has bigger score, and round it to 2 decimal digits using round function from NumPy library. So we can read that as binarized price, meaning that we actually starting to work with the classification task that we need to in the classification. Yeah, so we need to predict the discrete target variable. So, and basically we need to, first of all, to receive it, because our initial target variable is basically continuous for the regression problem. So we need to actually turn it into the binary that we can work with the classification task. So, and for that, we need to create a variable called above average, which is 1 if the price is above or equal to 152. Yeah, so let's go to that. Let's go to our homework. Yeah, so once again, I do the copy of the initial data frame to work with the classification task. So, and then basically we can check that 152 is actually mean of the data set. So, and we actually can create the variable called mean, which will be just calculation of the mean of the price. And then we create the feature called above average. Here are also a couple of ways how we can do that. So I use the function where from NumPy library to actually do the, let's say, kind of if condition. So we checking the basically the mean. Yeah, so we take the price and check whether it will be bigger or not than mean, and then if it's kind of bigger than mean, that it would be 1. And if not, it would be 0. So therefore, we getting the feature column. Yeah, so our target column with the 0s and 1s. So basically, this will be the discrete values for our classification task. So this means that we don't need the initial price column. We work all above. We will use train to split functionality from the scikit-learn library and model selection. So for that, basically, we remember that we need to split into the 60%, 20%, 20% for the train, validation, and test set. So how we can do that? So we can do it basically in 2 steps. So first of all, we are creating the 2 variables called train full, for example, and test. So we split it, the whole data frame, and select test size equal to 0.2. Yeah, so we already on the first iteration have the tests equal to 20%. And then we need to get the accordingly, so 60% for the train data and 20% for the validation set. So we do it once again. So we're creating the data frame called df train, for example, and df validation, and also specify the test size. In this case, it would be not 0.2, but 0.25 because we're already working with the, let's say, reduced amounts of the data set because we already saved this 20% in the test set. So, and if you calculate it, so you will receive the exact needed percentage. So 60 for train, 20 for validation, and 20 for test after this two steps of train test split. So kind of applying this function on our data. So yeah, after all this, we will reset indexes and saving the above average feature inside of the variables, just to use it afterwards. So then we go to the mutual information finally. Yeah. So for that, what we need to do. So actually, we can use the already existed function from the scikit-learn metrics package. So, and we can just import it like that. So mutual info score. And basically mutual info score, we will use our categorical features. So in our sense, it's a neighborhood group and room type. And we'll calculate the mutual info score for them. So basically kind of connecting them with our targets variable. So and calculating the score accordingly. So for that, we can create this small function, calculates mutual information and put inside the series. So it will return the result of the function itself. So basically, so it's kind of applying the series and the target variable. So we remember that we need to do that on the train set. So therefore, here is df train dot above average, which is basically the target variable. So then we apply this function to only categorical columns, categorical feature columns of the train set, and calculate the score. So basically applying our function. Then in the question, we need to understand what is the bigger score. So therefore, we can also use the function sort values in ascending equal to false order. Then we having the result. So here is our final data frame. So room type and neighborhood group. So basically room type, we see that it has bigger score, which basically, so basically this is the answer, yeah, for us. So the answer for question number 3 is the room type. Yeah. So, yeah, so any questions to that point? So, or no? So yeah, okay, then we can go further. And we need to remember to drop the above average column from the from our data frames, because on this particular stage we will solve the classification task, and we for sure need to kind of be kind of self-secured and kind of having the feature set without target variable and target variable kind of in a distinct variable. So for that, basically, if you remember the previous lections, so we use the del function. So this is basically the another approach how we can do that. So kind of like a pandas approach. So you can use the function called drop. So in this manner, so for example, you can select the data frame, then dot drop. So applying the function, and basically I'd like to drop. Yeah, so you can either kind of do it in this way or do it with the parameter called in place equal true. Then you don't need to make this kind of equal sign. Then you can do it in let's say one row without equal, without assigning. Yeah, and also, for example, if you would like to drop, let's say, 2 or more features, you can kind of save it into the lists. For example, feature A, comma, feature B, feature C, and then apply the drop on this list, and it will kind of remove, so basically drop all these features from the selected data frame. So let's go further on to the 4th question. And 4th question is basically our classification task. So we need to train a logistic regression model, which we'll take from the scikit-learn library. Remember that we have 2 categorical variables, meaning that we cannot apply them kind of straightforward, because that will raise an error into the logistic regression model. So when we need to converted into the numeric format. So basically using the one-hot encoding techniques that Alexei showed in the theory lections. Feed the model on the training set and basically specify the needed parameters from here and calculate the accuracy on the validation set rounded to the 2 decimal digits. So for the accuracy, we can also use the scikit-learn functionality for calculating the accuracy score. So let's go back. So this is basically the additional functions that we need to have. So we import them. So for the one-hot encoder, so there are also a couple of ways how you can do that. So, but we will stick with the theory lections, and we'll use dict vectorizer from the feature extraction scikit-learn library, logistic regression from scikit-learn as well, and also accuracy score. So here are our numerical features that we basically kind of save in the list. And then we prepare for the using of dict vectorizer. So we're creating the dict from the train dataset, combining categorical and numerical functions. So categorical we already saved before. So numerical we kind of saved right now in the list. So we just can basically concatenate them using the plus sign and using the function to dict with the specification orient records. So this is enough. Then basically we specifying the vectorizer itself and just feed it with this train dictionary. So just put it there. And then afterwards, after it's fitted, we can actually transform the train feature set. Yeah, so like that. And after that, so it's already applied one-hot encoder, and we can already going into the training of the model. So we kind of specifying logistic regression with the parameters that was in the homework. Solver, so C parameter and random state equal to 42. Then we just feed the model as we did before with the linear regression, model.feed on the training set. And then basically before calculating the accuracy score on validation set, so because validation set also contains the categorical features, we also need to do the same thing that we did before on training set, but on the validation. So we need to also perform one-hot encoder. This is very interesting that you need to see that in this sense, we don't need to once again feed it because we already fit it on the trained data. So we just need to transform. This is very important for, let's say this, for all of the pre-processing techniques, especially if you use, for example, scikit-learn transformers that you need to fit on the trained data and then transform on the, for example, validation or test set. So you don't need to feed once again to not to have, say, the kind of corrupted results in the end. And in the end, you have the validation set. So basically, you can just call the model.predict on X validation and receive the predicted target. And what you need to do after that, you need to call the accuracy score from already imported function from scikit-learn and round it. So it will 0.79. So basically the right result, right answer for this question will be 0.79.
Yeah, we have a couple of questions here. So first, the question was if this accuracy score works in exactly the same way as shown in the lectures. The answer is yes. So I'm not sure how exactly it's implemented inside scikit-learn. Probably something similar.
Yeah.
And then the other question is about, so there is a comment, and I think many of you had this problem that when you train a model, it outputs a warning. So Dmitry, why do you not have a warning here?
Yeah, because I use the this guy, so import warnings that filter warnings ignore, that we discussed briefly on the previous section. Yeah, so basically this helps you kind of not to have the kind of warnings in your code. So because I mean, for sure, if that would be the error, then kind of the code will stop. Yeah, but if it's kind of some minor warning, so basically using this approach will not just appear in your code.
Yeah. At the end, I prepared a small demo, sort of how to get rid of this. But in general, like if you saw this warning, it's fine. It's not an error. It just says that, okay, like I failed to converge. Sorry, but it actually finished. It actually trained the model. So there are actually coefficients. So it's in general, it's okay. And you shouldn't be worried when you see a warning like that. So it's fine. And as long as you have a validation data set and you can check your model on this validation data set and you can see that it's actually working, then you're fine. And
yeah, in this sense, it's just kind of saying you the information that maybe it's not the optimal kind of approach. Yeah, so it's just, let's say, the info, not the error.
Yeah, exactly.
So can we go
yeah, I think one more comment for those who tried it with liblinear. I also tried with a different solver, liblinear, and it works in the same way. So I was able to arrive at the same solution. And some people write that they had to use liblinear to be able to train it, because they used Kaggle, for example. On Kaggle, there is an older version, scikit-learn, for which, for some reasons, this solver doesn't work. So with liblinear, it was also fine. And this solver is just an algorithm that scikit-learn uses to find these coefficients, to find these weights. And so internally, yeah, maybe for some things, some solvers work better, for some worse. But for now, you shouldn't really worry about them too much. So this is a way to find these coefficients. And then, of course, you can go to scikit-learn documentation and read how exactly these solvers work if you're really interested in that.
Yeah, so let's go to the question number 5. So it's about the feature elimination. So let's read the question. So we have 9 features, 7 numerical and 2 categorical. So basically, let's try to use feature elimination technique. So what is feature elimination? So the idea that we kind of train the model with all of the features and then kind of take on each iteration one of these features, train the model and calculate the results. So basically, in our sense, it's will be the accuracy because it's a classification problem, and then we just need to save the basically accuracy on the each iteration, and also calculate the difference on each iteration to understand what which of the following features has the smallest difference in the overall accuracy. Yeah, so we have 4 variants here. So this is the 4 features, and also note that the difference doesn't have to be positive. So I think it's enough information for us, so we can start. So what we need to prepare. So we're preparing the features variable. So basically just concatenate the categorical features and the numerical ones. So creating, let's say, the big list that contains all of the features that we will work with, and starting with the feature elimination technique. So beforehand, we save the accuracy, so original score that we receive when we use all of the features. So basically, or equal to accuracy, meaning equal to 0.79. So, and then basically there are also a couple of ways how you can do that. For example, you can use also scikit-learn approach for that, for the feature elimination. But in this example, so we can basically use just a simple for loop and basically iterate like through all of the features. So for C in features, we basically copying the feature and then do the remove function. Yeah, so apply it to the each of the feature. So kind of on each of iteration. So basically on each iteration we remove one feature. So do everything the same that we did before. So we kind of train the one hot encoder. So using the vectorizer technique. So on train data. So fit it and transform, creating the train feature set, Yeah, and then basically apply it on our logistic regression with the same parameters, or feed it with a trained data set, and also do the same one-hot encoder transformation for validation and do the model.predict. Then we calculate the accuracy score. And then basically the most interesting part is the final one, so which we will print the C, so basically the iteration, meaning the number, or meaning the name of the feature, printing the original score minus score, which basically the difference that we need to check, and the score itself. Yeah, so score without this feature that we remove. And here is the result. So basically for all of our features, so we have the numbers, but we are not interested in all. We are interested only in 4 of them: neighborhood group, room type, number of reviews, and reviews per month. So, and we can check that the number of reviews, yeah, so this guy has the smallest difference. Yeah, so if we compare with the other ones, yeah, so this one, and with this one, so this is the smallest difference, meaning that it's the biggest accuracy score in the end, meaning that it's kind of has the smallest difference, has the smallest impact on the final results of the accuracy. So, and basically the answer for this question is the number of reviews.
Yeah. So what I want to add is when I did this exercise as well. So for me, number of reviews was actually negative, and it means that if we remove this feature, our model becomes better. So the accuracy after removing the feature is actually better than when this feature existed. That's why we have this note saying that it doesn't have to be positive, and if this difference is negative, it's actually good. Then I also saw that like I'm looking at the solutions, and actually we have these 2 features: so number of reviews and reviews per month. And in the answers, it's like 50-50. So many people selected number of reviews or reviews per month. And it turned out that with some settings, because I know many of you had problems with warnings, so you tried to get rid of this warning by increasing the number of iterations or trying different solvers, or I don't know, doing some other things. And sometimes under different settings, you end up with a different feature. So sometimes it's reviews per month, for example. I was also able to reproduce this. So I think with liblinear and something else, I don't remember. Like I was able to also get this answer. So that's why I think for this particular exercise, the important thing here is that now you know how to do feature elimination. So now you can do, let's say, a for loop, and you can remove a feature. And that's why we will count both number of reviews and reviews per month as correct answers. Because I think they are also correlated, right? We saw that they're the most correlated pair of features. So that's why it makes sense that, we already have information in one variable that like they're telling us basically the same information. So yeah, we will count both of these answers as correct. So yeah, don't worry if you selected the other one, reviews per month, you will also get a score here. And I'm looking at the questions. I don't think so. There is a question: what is C? What is C? So Dmitry, what is the C parameter?
So basically, it's the parameter for the logistic regression. So basically, you can select it and like change. Therefore, basically, it will, let's say, it will give you more kind of. It will make your model more strict in the prediction in terms of the probability and that kind of probability calculation or not. So
this is basically regularization.
Yeah, so
that we covered.
Yeah,
we covered for regression. This is similar to this R parameter we had in the previous week. Yeah, I think we can move on.
Yep. Okay, then basically the question number 6, it's going back to regression problem. Yeah, because beforehand we use kind of manual regression techniques, so to say. So right now we will use this scikit-learn approach. So we need to revert to the original column price and also apply log transformation on that. We need to use the rich regression on the training data and also specify the parameter for the regularization. So it's called alpha parameter in the scikit-learn. And then basically check the RMSE, root mean squared error. So and select the kind of the minimal RMSE. So and basically the associated alpha. So and there's also the note, if there are multiply options, select the smallest alpha. So let's go back. So for that, we need to do a bit pre-processing once again. So we need to take the initial price and apply the log transformation. So it's the same as in previous lections. So also we do the train test split in 2 steps to get the needed distribution, 60 to 20 to 20. So it's like that. Also the same approach as before, reset index and saving the price target variable values. And then in this example, I just use delete function. We can also use the drop as well to drop the target variable from the data frame. And then the rich regression part. So once again, we will apply the same one-hot encoder techniques. So I will not comment it on that because it's the same as before. And before actually doing it, we need to import the rich regression. So it's called rich from scikit-learn linear model library and mean squared error. So basically it's the same mean squared error that we calculated before. So, but it's already in scikit-learn. So therefore, to actually have the RMSE, so we need to use mean squared error with the function that will take the root of that. So for example, we can use the numpy sqrt function. So in this all together in the combination will result in RMSE that we had before in our previous section. So it's also one of the approach how to do that. So, and also like the quickest, I think, idea how to do that, it's also create the for loop with the candidates for our alpha variables. So here they are, you can see, so 5 of them. And then basically specifying the model called rich, so which will have the alpha equal to A. So we will kind of go through iterations through all of these parameters and check it with a random state equal to 42, as also in the conditions. Train the model.fit on the train set, predict on the validation set. So we already do the transformation, which is fine, and calculating the score. So as we discussed, so we need to round the score to the 3 digits. So here, how we can do that. And just printing the results. So you can see the results here. So basically the alpha variables with corresponding RMSE scores. And we actually need to receive the minimal RMSE. So and take also the minimal alpha in the case if they're equal. So we have this case. So and therefore we need to be alpha, which in our case will be 0. So the answer for question number 6 will be 0.
And I saw in Slack that sometimes people would remove this rounding to 3, and then they would see that okay, for it actually is different. So this was, if you did this, you didn't get a correct result. So you should have stick to the so to the conditions, to the homework. So you shouldn't have removed the rounding here. And so the reason here is sometimes some data sets don't require regularization. And alpha here, so rich regression here is the same, almost the same thing as we did last week, except here it's a scikit-learn implementation of regression, and alpha is kind of similar to this R thing that we had. Yeah, so here it means that we just don't need regularization.
Yep.
Okay, we have some questions for the previous question. So the question about the previous question was, in practical scenario, what would we do when we see that some features like they let's say have negative difference, or they are very small? So what would we actually do with these features?
So in case if the mutual info would be small, or what does mean? Or...
Yeah, so let's say we did this and we see that for some, sorry?
So the difference is small, or
yeah, the difference is small, or even it's negative. Like what would we do in this scenario when we see that for, let's say, a number of reviews, the difference is so small that it doesn't really affect the model, or even it's or in cases when it's negative, it makes the model worse. Like what do we do with this feature? Do we remove them from the model?
So I would say that this will give us really important information about how we need to select the features. So for sure, we need to use this information to be able to select correctly. I would also say that in a perfect case scenario, that it should be the combination of a couple of the approaches. For example, in this sense, so you can do the feature elimination, so it's like in this example, but you also can, let's say, combine it with a statistical approach. So for example, in our case, it's the classification problem, and we are trying to, for example, let's say we're working with a categorical feature, so let's trying to understand what will make effect on the target variable or not. So therefore we can use the statistical criterion, so for example chi-squared score, to actually see whether it will have the effect on the target variable or not. Yeah, so for example, for the numerical ones, we can use the t-test, for example, and also to understand whether it will be significant or not for the results on the target variable. And then usually you combine these approaches and see, for example, if a couple of these approaches says that it's not really a valid feature, yeah, so for your data set, so usually you can just remove it, yeah. Or if it says that it's kind of having some information that you can use in the prediction, so for sure you will need to stay.
Mm-hmm. And there's also a question, why did you take test set 033 in step 2 for question 6? So I think that was probably just a typo. Like if you scroll a bit up, like when you do the split in, yeah, up, like here, cell 32. So maybe it's just a typo.
Oh, I think, yeah, it's typo, yeah. Mm-hmm.
Yeah, but I did this with 25% and it was fine. So like this data set just doesn't really, at least for this kind of model, for this data set, it just doesn't need.
Yeah, and for this question especially, so when you're talking about the regularization, so we can see how difficult to change the value here. Yeah, so for the RMSE, so meaning that if you will change this parameter, so nothing will kind of change dramatically.
Okay, thanks. So do you want to add anything, Dmitry?
No, I think it's all clear, I guess. I hope.
Yeah, so let me just quickly check chat. Yeah, so what I want to show now, I see that we don't have a lot of time. I want to quickly show you how you can get rid of this error. So if I can share my screen. So, okay, now let me share my screen. So this error that many of you had, so this convergence warning. So the reason it can happen is in the previous week for finding weights for linear regression, we used the normal equation, which finds the solution in just one go. So you take the formula, you encode this formula with NumPy, you run the code and you get the weights, right? So, but logistic regression is a little bit different. So for logistic regression, here's a bit of math. You don't need to really understand what's going on. So for logistic, for linear regression, we so what happens when we do a normal equation? Internally, it optimizes this function. So it actually optimizes the mean squared error. So like for every prediction, so something like that. So this is what normal equation optimizes. So by optimizing, it tries to find such W's that this thing becomes minimal, as small as possible. So this is what solvers do. So all these solvers that we saw, they take some, it's called loss function, and they take this loss function and try to optimize it in such a way that these parameters W weights, they are as small as possible, right? So this is for a linear regression. And for logistic regression, it's something like this, right? So it's a more complex formula. It's called log loss. And so we don't need to really understand what's going on here. Right now, of course, if you want, you can read about this. But this is what logistic regression is trying to optimize in order to find these W's, these weights, right? And the way it does, so we cannot just have something like normal equation that takes this formula and finds the solution in one go. So what happens inside? So this is we use iterative algorithms for finding the best W. So what it means is that we take this W and we do it in, let's say, I don't know, let's say 100 steps. So at each step, we try to change W a little bit. So we look at, we try to change it a little bit, a tiny bit, to see which W leads to smaller loss function, right? So we change it a little bit by little bit until, let's say, after 100 steps, we find the final W, right? So here, when we see something like this, convergence warning, it means that this solver tried to minimize this loss function. It did this for, I don't know, 100 iteration, or what is the default value, and it thinks that it hasn't converged yet. So there is still, like it could still improve the solution. And the reason for that, the reason it happens is because we have, let me just show you. So we have, let's take our data frame. It's not defined. Okay, I think it's called data. Yeah, so if we look at our features, let's take numerical features. So these features, they are on a different scale. So if we, what I mean by this, so if we take a look at this latitude and longitude, so they're in this range, so it's between 40 and minus 73, for example. For this minimum number of nights, it's between 1 and 10. Right, so here is between 0 and, I don't know, I see here we have 270, so it could be 300, for example. And here, again, this is different, so it can be maybe between 0 and 10, something like this. So all these features, they are on different scale. And this is actually the reason this is important for iterative algorithms, because here, like let's say when we take W, right? So W consists of W1, W2. I think I use Zoom. So just one moment. So W consists of W1, W2, Wn, let's say. And if we have features on different scale, then when we try to move this in iterations, right? We try to find the best W here. So what happens is that for this feature, if it's like latitude, longitude, so for these features, the size of the step is different from these features, right? Because they are on different scale. And this is confusing for such algorithms for that use iterative approaches. So this is the reason we saw this warning. And one way of fixing this, it's to actually, for these features, is to bring them on the same scale. And for that, we can use different scalars in scikit-learn. And this is not something you had to do in the homework. I'm just showing you in case you ever need this. So there are different scalars, like standard scalar, which you can read about them in scikit-learn documentation. So standard scalar, min-max scalar, there are different ways of scaling features. And for example, here, if I use standard scalar, so it's also a transformer like dict vectorizer. So you need to fit and transform it. And for example, this is how, let me just execute it. So for standard scalar, let's say, so the first one was the latitude or longitude, I don't remember. So you see that, where's the numerical? You see that instead of 40, now it uses -162, right? So it changes them a little bit. And with that, here I also wanted to show you how to use one-hot encoder. I think I don't have time to explain it now. I'll just share the code. You can have a look at this. So in the homework, we use dictionary vectorizer, but you can also use one-hot encoder. It's a bit more complex because for one-hot encoder, you need to then process categorical features separately. And here, this is what we actually needed. So for numerical feature, we applied scalar. For categorical feature, we applied one-hot encoding. And then what we needed to do is we have two set of features. So we have one feature matrix with numerical variables, another feature matrix with categorical variables. Now we need to put them together. So in this X train, so I think I need to execute that. So one-hot encoding. So this one-hot encoder works in the same way as dictionary vectorizer, more or less. And so now we put them together into one matrix. So we have this one matrix. So first we have numerical, then we have categorical features. And when we execute this with default, I don't know what's happening. Because it's, you'll have to believe me that it works. I think because I haven't been binarized the variable here, but so this one will not give a warning. So because of that, if you try it with min-max scalar, it will still give a warning. And to be honest, at the end, the accuracy is not that different. So it's a little bit better, but I don't think it's actually worth the troubles of going through that instead of just using dictionary vectorizer. But this is something I wanted to show. I don't know if there are many questions. So what I'll do now is I'll just go through the questions from Slido. Okay, let me share my screen again. Okay, the first question is, shouldn't we automatically scale the features before using the model? I think I just answered that question, right? More or less. Dmitry, what do you think? Do we always need to scale features or not?
It's really depending on the model that you use, but if we're talking about the linear model, then for sure. So you need to scale it before actually you. So there can be the situation that they're already more than less scaled and you don't need to do anything. But overall, yeah.
And for this particular data set, we saw that we have features on different scale. And for the model, it could be confusing, like when we use iterative solver to find the best solution, the best weights. It can be confusing for these kind of solvers, for iterative solvers. Okay, also why not use PCA to discriminate between important and less important features? We didn't really cover PCA. So PCA is, I don't know how to explain it in a few words. Maybe Dmitry, you know how to explain it in just a few words. Oops, I think we lost Dmitry. Okay, then I'll try to do this. So basically, this is a feature. Like PCA finds a way to combine, to create new features from existing ones. And usually when you use PCA, the features that you get, they're less easy to interpret. Anyways, I don't want to go into much details about PCA, so you can just look it up using PCA for feature importance. And then you can ask questions in Slack. Okay, can you talk a little bit more about rich regression? So are there other regression types that are popular in data science? So rich regression is an implementation of regression. So we have linear regression, which is regression without regularization. Then we have rich regression, which is regression that has regularization. Rich regression is very similar to what we had in the previous lesson. It's more optimized. Yeah, other regression types or regression models, let's say, you can have tree-based models that we will cover soon. Then neural networks can also solve regression problems. So yeah, there are definitely many other models that you can use for solving regression. And I'm thinking maybe for the week when we will do train tree-based models, we will also use we will also solve a regression problem using trees. Okay, Dmitry, are you back? Okay. Is the regularization strategy of adding small values to the main diagonal of the feature matrix related to rich, lasso, or other regularization techniques? Yes, so it's very related to rich regression. So there is a proof, mathematical proof, that shows that it's exactly the same. It's a bit hairy, like it's like there is a lot of derivations that you need to go through to show that they are equivalent. But yeah, they are the same. Lasso is a bit different. Yeah, I don't know if I should go into details now. It's a different way of regularizing. So with Lasso, one of the key features of Lasso is that it forces some of the weights for your model to be 0. Like if a feature is not important, it makes it 0, while for each, it just makes it very small. So yeah, but in short, they are very related. How to go about choosing the regression models and the corresponding parameters if that we fed as arguments, such as C, alpha, etc. How can we learn more about this? So this is why you need validation set. So you use validation set exactly for this. So you use validation set to try different ways. Like let's say you want to try different C's, or you want to try different alphas, you use validation set for that. Or you want to get rid of some of the features and try to see if the score improves or not, you use validation set for that. Also this week, we will talk more about evaluating models, evaluating binary classification models in particular. And we will talk about cross-validation, k-fold cross-validation that are also useful for that. But in general, just use your validation set for that. How to get better encoding? I understand all in your lectures, but when it comes to implementing in Python, it takes quite a lot of time. Just you need to practice. I don't think there is a better way to do it. What are some most popular applications of logistic regression in data science? So one thing that immediately comes to mind for me is click prediction. So let's say you go to some website and then there is a banner. And what happens behind this banner is there is a model that predicts that what is the probability that this user who comes to this web page, meaning you, what is the probability that you will click on this banner? And usually there is some sort of linear logistic regression under the hood because they are pretty fast. So for advertisement, they're used quite a lot. Like when, especially when we talk about real-time advertisement, like when you enter a website and you immediately get an ad, this is where linear models such as logistic regression are used. How many submissions were there this week? I think around 200, 204, I think. Yeah, something like this. Is there any threshold or some standards about how many features that we can use to build a good model? I don't think so. So it really is problem dependent. Sometimes adding a lot of features can hurt your model. So you don't want to add too many features and just hope everything will work out. So you need to be careful. Sometimes adding a feature can result in model degradation, but there is no standard. So you just, it really is problem dependent. For some problems, you need to have a few features. For some problems, you need to have a lot of features. So for example, we talked about advertisement, online advertisement. And for these models, they use, I don't know, millions of features because like the device type. So they use a lot one-hot encoding. And when you use one-hot encoding, you get like millions of features, right? So it's really problem dependent. I want to know the theory behind machine learning. Could you recommend a book or a course that covers that part? I think I did recommend a course once. So you can watch a course on Coursera by Andrew Ng. It's called Machine Learning. So it covers theory quite well. So the theory is also on intuitive level. So the math there is comparatively less difficult comparatively to textbooks. And then, of course, you can get textbooks. So good textbook is Elements of Statistical Learning. It's really good. There is a lot of math or pattern recognition. I think there is a book called Pattern Recognition or Machine Learning Probabilistic Approach. That's another book. So one is Bishop, another one, the author is Murphy, and they're very mathematical. So there is a lot of math. You really need to have, I don't know, a couple of years of calculus in your background to be able to understand that. But if you don't have that background, a course by Andrew Ng is good. So let me cover just 2 last questions. So when to use test data set? So we didn't use test data set for this homework, but actually this is you use that when you trained your model. When you did all this validation, you found the best parameters, you found the best set of features that you want to use, or you found the best model, you compared multiple model perhaps. And then what you do is you combine your train and validation data set, train one bigger model, and then you check it on the test data set to make sure that everything worked out. So check the lectures, I think in every week, starting from week 1st to the 3rd week, we covered that. So just make sure to check that. Is there any easier way to do one-hot encoding without using dict vectorizer? I think dict vectorizer is the easiest one. And this is the reason I thought it's good to use for this for this course. So let me show you. So this is how you can use one-hot encoder. And I also showed you that you need to do this column stack, which makes it a bit more difficult than using dict vectorizer. So with dict vectorizer, you just throw everything in and you get a matrix out, which I find easier than one-hot encoder. So I'll share this code as well. You can take a look at this and decide what is easier for you, one-hot encoder or dict vectorizer. So I think that's it. So we should be wrapping up. Thanks a lot for joining us today. And I don't know what happened to Dmitry. I hope everything is fine with his internet connection. So yeah, have a great week and enjoy this week's homework. Goodbye.